Hi, I'm Wang from HKUST. Today, I will present our recent work title, A Fast, Scalable, and Accurate Rate Limiter for RDMA NICs. This is a joint work with ByteDance. We first introduce what is the rate limiter, why we need it, and how it works. There are some policies in RDMA NICs. For example, congestion control policies precisely allocate bandwidth across many flows and help mitigate the network congestion in high-speed networks. And the traffic isolation policies are required by practical cloud management. These policies output the rate limit for each flow, like 100 Gbps for flow 1, 10 Gbps for flow 2, and then ask the rate limiter to enforce these policies. Specifically, the rate limiter does two things. First, it enforces a specific rate on each flow. Second, it injects inter-packet gaps to smooth the traffic. The rate limiter then participates in the RDMA NIC's data path, determine which flow occupies packet to send next, and when to send it. It first calculates the transmission time of the packets among various flows, then sort the packets to find the one closest to be sent and send it on time. Then we discuss the desired properties of the rate limiter. First, end-host rate limiting desires a rate limiter to be accurate and scalable. High accuracy means the rate limiter should precisely enforce the given rate on each flow and inject the inter-packet gaps to smooth the traffic, preventing burst. It often demands nanosecond level precision, and inaccurate rate limiting can result in traffic bursts and worsen network congestion. Also, the rate limiter should support a wide range of rate limits, for example, from 100 kbps to 100 Gbps, and allow for fine-grained adjustments instead of some several fixed values. And high scalability means the rate limiter must support rate limiting for tens of thousands of flows at end host, since the memory and computing resources in hardware are limited. RDMA NICs desire a scalable rate limiter that can support a large number of flows with low resource consumption. Besides accuracy and scalability, RDMA NICs desire the rate limiter to be fast. RNICs, which offload the RDMA transport protocol, are known for their high performance. For example, they can achieve a high packet rate of 110 million bps using a single NIC port, transmitting a packet every 9 nanoseconds. And RNICs need to integrate the rate limiter into their data path to deploy it. So the performance of the rate limiter directly impacts the performance of the RNIC. If the rate limiter is low, it will reduce RNIC's performance. So the rate limiter needs to be fast enough to achieve a high packet rate, for example, transmitting a packet every 8 nanoseconds. Also, a high packet rate helps it to utilize a higher link bandwidth like 400 Gbps. However, existing works fail to meet all these demands. We first talk about the commercial RNIC Bluefuse performance anomaly when enabling rate limiting. As shown in the figure, we observe up to 13% throughput degradation when enabling rate limiting for more than 10,000 flows. We used the programmable congestion control framework to test the rate limiter, and the detailed setup can be found in the paper. This performance anomaly indicates some potential performance issues with BF3's rate limiter, though BF3 is a black box and hinders further analysis. Recent studies, SIGCOMM' and PILE, implement scalable and accurate rate limiters for end-host NICs. However, it is not fast enough. As shown in the first figure, SIGCOMM' and PILE only achieves 13% packet rate compared to RNIC when supporting 16,000 flows. As shown in the second figure, when given a higher MAC capacity, for example, 400 Gbps, this low packet rate makes it insufficient to saturate the link bandwidth. We then systematically analyze the workflow of Scenic and Pile and find that they follow a monolithic design. Specifically, it first sorts all flows and schedules the nearest one to be sent. Then it fetches and transmits the nearest flow's head packet. Such flow level rate limiting is accurate, scalable, but slow, because it transmits only one packet after sorting all flows, and sorting many flows becomes the performance bottleneck. Sorting many elements quickly in hardware is inherently challenging. The reason is that the increasing number of flows to be sorted increases the complexity of the combinational circuits, then decreases the maximum clock frequency of the sorting circuits. The sorting rate is the clock frequency divided by the cycles per sorting operation. For example, with 200 million Hz clock frequency and 2 cycles per operation, the sorting rate is 100 million packets per second. As a result, the sorting rate also decreases as the number of flows increases. The figure shows the maximum clock frequency that Scenic and Pile can achieve decreases when the number of flows increases, which causes Scenic and Pile's a low performance. Instead of tackling the challenges of sorting, maybe we can rethink the workflow to improve the performance. We notice that the workflow of previous monolithic rate limiting consists of 2 steps: flow scheduling and packet transmission. Thereinto, flow scheduling seeks scalability and packet transmission seeks accuracy and performance. This provides a chance to renovate the workflow and design a hierarchical rate limiter that meets demands separately. We inherit the flow level rate limiting to solve tens of thousands of flows and schedule the nearest flow. Once a flow is scheduled, we can fetch multiple packets. Then, we additionally apply accurate and fast packet level rate limiting to this batch of fetched packets. We filter packets close to be sent and drop the left. This helps reduce the number of packets to be sorted. Finally, we sort these imminent packets among flows and transmit. Based on this idea, we designed Tensor. Tensor's design goal is to improve the performance while maintaining accuracy and scalability. To achieve this goal, we follow 3 design principles. First, enable the transmission of multiple packets after sorting all flows to improve packet rate. Second, utilize the time-based rate limiting algorithm and transmit the packets based on the calculated timestamp to ensure accuracy. Third, save memory and computing resources in hardware as much as possible by avoiding unnecessary buffering or too complicated data structures to improve scalability. Guided by the above principles, Tensor designs a 2-tile hierarchical rate limiting by first applying scalable flow level rate limiting, followed by accurate and fast packet level rate limiting. And we integrate Tensor into the Ionic architecture by replacing the original QP scheduler. As shown in the figure, Tensor's hierarchical design consists of flow level rate limiting and packet level rate limiting. Here is the workflow. First, sort packets. The flow scheduler first sorts tens of thousands of flows by their head packet's transmission time and then identifies the latest flow. Second, monitor and schedule. The flow scheduler monitors the current time and schedules the latest flow when the current time approaches its transmission time. Next, fetch packets. The flow scheduler fetches multiple packets for the subsequent packet level rate limiting. Next, compute transmission time. After fetching the packets, the time calculator computes the packet transmission interval and time based on the packet size and rate limits. Next, filter imminent packets. From fetched packets, the packet filter picks imminent packets whose transmission time is close to the current time and hence close to be sent. The rest of the packets are dropped and refetched next time. Then reschedule. The packet scheduler notifies the flow scheduler to update the head packet transmission time and reschedule the flow on time. Next, sort packets. The packet scheduler then sort these imminent packets based on the transmission time. And at last, monitor and transmit. The packet scheduler monitors the current system time and transmits the nearest packet on time. We then introduce integrating Tensor into RNIC architecture. Figure shows a typical RNIC architecture consisting of 4 parts. QP scheduler schedules QPs. DMA engine fetches OKs and data from host. Transport realizes the RDMA transport and generates the packet header when the payload arrives. The basic NIC sends and receives packets from the network via the MAC interface. We integrate Tensor into RNIC by replacing original QP scheduler with the hierarchical rate limiter. There are 6 submodules. Emacs gathers all scheduling-related events like doorbells and maintains a list of active QPs. The QP scheduler uses the timeline module to sort QPs, and uses the timer to monitor scheduled QP, and then fetches OKs and stores in the OK buffer. The packet scheduler processes the fetched OKs, computes the transmission time for the packets in these OKs, filters the imminent packets, and sorts them in the timeline module. At last, the timer notifies the packet scheduler to consume OK and transmit packets on time. In Tensor, we use the timeline module to sort QPs and packets. There are various sorting stages with different requirements. For example, QP scheduling deserves high scalability and medium performance, while packet rank sorting deserves low scalability but high performance. So Tensor chooses the suitable data structure for each stage and uses the combination of data structures to collectively meet the requirements for accuracy, scalability, and performance. Dedicated data structures include pipeline heap, timing wheel, and register error. In summary, Tensor is fast as it enables multiple packets per sorting transmission, improving the packet rate. Now the maximum rate has increased from sorting a few thousand flows to sorting a few hundred packets. For scalability, Tensor is resource efficient and achieves high scalability. No packets are stored in hardware and only a few OKs are stored, about 500 bytes for all QPs. In terms of accuracy, Tensor transmits packets precisely based on the calculated transmission time and can enforce the rate limits and prevent traffic burst. We implement the prototype of Tensor using Intel FPGA, running at a clock frequency of 215 million Hz. We realize 16,000 QPs in Tensor, and the resource consumption is broken down in the table. The resource consumption of Tensor is considerably low, and it can achieve high clock frequency, thereby making it friendly to get integrated into various architectures. For the evaluation part, we first show that Tensor achieves a high packet rate. We measure the aggregate throughput of multiple flows while increasing the message size. As shown in the first figure, Tensor can saturate the 100 gigabps link bandwidth with a 128 byte mask size, achieving 125 million packet per second high packet rate when supporting several thousand flows, which is 3.6 times higher than sending and pile. We then measure the maximum clock frequency that the rate limiter can achieve, varying the number of supported flows. As shown in the second figure, Tensor achieves a high clock frequency and shows a slower decline in frequency as the number of flows increases. We also compare Tensor with BlueField 3 in terms of the aggregate throughput while increasing the number of QPs. As shown in the third figure, Tensor consistently achieves line rate without performance anomaly. Meanwhile, Tensor achieves high scalability. As shown in the figures, Tensor shows very low resource usage. Even when supporting 16,000 flows, the computing resources used is less than 5% of our FPGA, while the memory resources is less than 1%. In comparison, sending and pile consume 3 to 13 times more resources when supporting 16,000 flows. In addition, Tensor achieves high accuracy. We evaluate Tassel's accuracy by configuring rate limit ranging from 100 kbps to 100 gigabps for a single flow. As shown in the first figure, Tassel accurately enforces any given rate, and the Bluefield 3 supports configuring rate limits from 200 kbps to the line rate. But we measure the actual minimal rate it achieves is about 400 kbps when setting a rate of 200 kbps. We then demonstrated that Tassel can precisely enforce configured rate limits for tens of thousands of concurrent flows. As shown in the second figure, Tassel's accurate rate limiting enables each flow to achieve the configured rate precisely. When the aggregate rate exceeds the linker rate, Tassel can proportionally adjust the flow rate. As shown in the third figure, when the aggregate rate is 200 gigabps, which is twice the linker rate, the rate achieved by each flow is just half of the configured rate limit. To summary, we present the design and implementation of Tassel, a fast, scalable, and accurate rate limiter for RDMA NICs. Tassel's hierarchical rate limiter combines scalable flow level rate limiting with fast and accurate packet level rate limiting, thereby meeting all design goals at the system level. With Tassel, our NICs can precisely allocate bandwidth resources at end hosts. We hope this can inspire more innovative protocols in high-speed networks and domain-specific networks aiming at a congestion-free data center. For example, AI training clusters can leverage the predictability of the training traffic to assign the sending rate among GPU pairs and avoid congestion. Thanks.